All right, so chapter 2, what we'll do is, in physics, a physics law is expressed as equations. Okay, so we use mathematical objects to express physics laws. So, for instance, I'll show you a law. Okay. All right. So, for instance, here is a kinematic equation. We wouldn't call it a law, that would be saying too much. But all this is saying is, see, this is the final position of an object. This is the initial position vector of the object. That is the initial velocity vector. That is time. That's the acceleration. Okay, and this kinematic equation is valid as long as A is constant. That is, it's not time dependent. Okay? So this is just a statement that here's your final position if this was your initial position and that was your initial velocity and all that, given the acceleration. Okay? Now here's what we are interested in. Okay, we talked about apples on the left-hand side and apples on the right-hand side. Okay, so just looking at it mathematically, here is a vector on the left-hand side. So that right away tells you that on the right-hand side, every term had better be a vector. You can't have a scalar, or you can't have a higher dimensional object. You can't have a matrix, for instance. And that's all we're checking. Okay? So this is a vector. Well, this is a vector. This is a vector, but here's a scalar multiplying a vector. And you learn that a scalar times a vector is a vector. This is a vector. That's a scalar multiplying a vector. Half is a scalar as well. So they're all vectors. So on the right-hand side is you have the sum of three vectors, which is a vector, and we'll learn all of that. Okay. So this equation is potentially, well, at least dimensionally it is correct. Okay. So for instance, this, if you replace this by, let's say, 5, that's still dimensionally correct, but that equation is not right. Okay. So, so right now, okay, so what we have in the back of our mind is physics equations or facts are expressed as mathematical equations. Physics facts or laws are expressed as mathematical equations. And we just want to make sure that the equations are kosher. Okay? So for instance, if somebody gave you this equation, I'm just, okay. You don't have to know what this is, but this, you know that this is not a vector, it's a higher dimensional object, and this equation is not right. Okay? This is apples on the left-hand side and something else on the right-hand side. Okay? So this is an equation that Mr. Einstein is famous for. Just a bunch of symbols. That's what he's most famous for. This is a 4x4 matrix, okay, a function of space-time. See that the two indices, okay, they go from 0 to 3, so they have 4 dimensions. So this is a 4x4 matrix. That's a 4x4 matrix. That's a 4x4 matrix. It's cool. Okay, the equation is cool. What this equation tells you is this side describes how space-time is curved. The curvature of this thing is described here. And what the right-hand side tells you is what curves makes it curved. Okay, so this is a flat space-time. Okay, just okay. You throw this, that curved it. So that's what this is. The right-hand side tells you the distribution of stuff, energy, matter and energy, that is curving it, and this is the curvature. All right, anyway, that's just trying to motivate the chapter. But okay, so what we're going to learn is we'll learn a mathematical object called vectors. Okay, and whenever you learn about any mathematical object, like say when you learned about numbers, how did you get to know numbers? I'm sorry? The way you got to know numbers was you learned how to add them, subtract them, multiply them. That's how you get. So that's what we'll do. This entire chapter, we'll learn what vectors are. Okay, we'll introduce a new object vectors, and we'll learn how to add, subtract, and multiply them. 3 things. All right. All right. So why are we learning this new mathematical object? Okay. It turns out that so vectors are quantities that have magnitude and direction to them. You all know that. So quantities like forces, velocities, acceleration. So these are all quantities that you'll learn in this class. Momentum. So they're all quantities that are represented by vectors. These are quantities that have magnitude and direction to them. Okay. There are other quantities you learn. So these are vectors. Okay. And there are other quantities, so like temperature, pressure, mass, and so on, where you just need one number to specify them. Okay? And those are scalars. All right, so we are learning about this new object not just for fun. We'll be using them because there's a whole bunch of quantities that are represented by vectors. Okay. All right, for a scalar, all you need is one number. How many numbers do you need to specify a vector? I'm sorry? 2 to 3. Okay, so it depends on the number of dimensions you are in. Okay, so if you are in n dimensions, 1 for the magnitude and n minus 1 for directions. So if you live in an n-dimensional world, you need n numbers to specify the vector. And they're an ordered set, but we won't get into all of that. Okay, so for instance, our friend here said 2 to 3 numbers to specify a vector. So you need 2 vectors if you're in 2 dimensions, 3 numbers if you're in 3 dimensions, and so on. Okay, so if you live in a 2-dimensional world, vectors are denoted by directed segments. Okay, so one number for the magnitude and 1 for the direction. So that's 2 numbers in 2 dimensions. Okay. Okay, let's do a 3D version. Okay, so there's many ways to specify the directions, but the standard in physics is there's one angle, okay, and then we'll project that, and this is the other angle that physicists like to do. Mathematicians do it slightly differently, but okay, so here are the 3 numbers that the physicists choose to do. So like I said, 1 for the magnitude and n minus 1 for the directions. Okay. All right. So what are we studying? We are studying a new mathematical object called vectors. And how many numbers do you need to specify it? N numbers in n dimensions. Okay. Vectors are denoted by directed line segments. Okay, so this is Of course, we can't draw a 5-dimensional vector. We are drawing 2-dimensional vectors, so you have an intuitive understanding of stuff. Even 3-dimensional vectors are harder to draw. Okay? Vectors are denoted by a letter with an arrow on top. Okay? So this, if the arrow is missing, that we are trying to convey the magnitude of that vector, and the magnitude of the vector is also written with absolute value signs. Okay? Here's the first, so here's a displacement vector. The displacement vector is the following. Let's say here's your initial position and there's your final position. Okay. Now it doesn't matter how you got to the final position. Your displacement vector is a vector pointing from the initial position to the final position. Okay. So there's your displacement vector. So let's say you started at home, you went to the library and came back home. What's your displacement vector? 0. Okay, so it's, you have to be a little more precise. It's the 0 vector. What is the difference between 0 and 0 vector? I'm sorry? Well, it depends on how many dimensions you are. Let's say you're in 3 dimensions. Here's the 0 vector. There is 3 zeros. Okay, so all the components are 0. Okay, anyway, so this is your first physical vector. Displacement vector is from the initial position to the final position. Okay, so here are some things that that are intuitively clear. So let's say here is the vector A. 2A just means, a vector twice as long. Okay, so, but here's what's going on underneath. So there is a scalar and there's a vector, and you intuitively understood a vector is a totally different beast, a scalar is a different beast, and I just multiplied them and you understood it. So that was intuitively clear. Okay, so 2A is that minus 2A, the negative sign, also you intuitively understood, is a vector pointing in the opposite direction. All right. Now, what is 4 plus 5? 9. All right. Now, it turns out that if you add 2 vectors, okay, B equal to, oops. Okay, in general, if this is 4 units long and that's 5 units long, this is not 9 units long. Okay? It can be anything. It can vary from, if this is 4 units and that's 5 units, it can vary from anywhere from minus 1 unit to 9 units long. So the length of that, okay? All right, so we will learn how to add vectors. They add differently. They are different beasts, so they'll add differently, okay? This is the only time when they're collinear and pointing in the same direction, they'll add up to 9 units, okay? All right. Two vectors are equal to each other if they have the same length and they're pointing in the same direction. Okay. Now this is true only in, well, no, I don't want to say that. Okay, so 2 vectors are equal if they have the same length and they are pointing in the same direction. So physically what this would mean is, for instance, if you're going 50 miles an hour north on Nova Road and 50 miles an hour north on I-95, your velocity is the same. Okay? Okay, so we are learning about vectors and new mathematical objects. What we want to learn is how to add them, subtract them, and multiply them. Okay, so here's a first intuitive way of here's a way to add vectors, which is easy to remember. So if you want to add two vectors, here's vector A and B. Remember, you can move a vector parallel to itself. So what we'll do is we'll move this B, the tail of B, onto the head of A. And the sum of the two is from the tail of A to the head of B. So that's how you add vectors. Okay? So this is a graphical method of adding vectors. This is not a practical way of adding vectors. This is a good way to remember it. Okay? A useful picture to have. Now that you've learned this, it's no problem. You can now, you know how to add 1,000,000 vectors. Okay, here's how you add 1,000,000 vectors. Okay, so let's say you want to add A, B, C, D, E. You do the same thing. There's A, B. You keep adding tail to head. C, D, E. And the resultant is that way. Okay. All right, so again, in mathematics, you want to study various properties. 4 plus 5 is the same as 5 plus 4. Okay? This law is the commutative law of addition for numbers. Okay? So you want to check and see if your new object obeys that. Okay? You want to see if A plus B is equal to B plus A. Okay? And it turns out that it is true. Okay? And so you see this is A plus B, that's equal to C. And this is B plus A, that's equal to C. Okay. All right, again, so you do this in all your math classes. When you learn about matrices, you'll learn how to add matrices and so on. Have you guys done matrices yet? Okay. No. So that's all we're doing here. You saw that 4 plus 5 plus 3 is 3 plus 4 plus 5. It doesn't matter what order you add them in. You can add 4 and 5 first, or you can add 5 and 3 first, or you can add 4 and 3 first and then add 5. It doesn't matter. Okay, you'll get the same answer. It turns out that is true for vectors as well. Okay, so if you're adding a whole bunch of vectors, you can add them in any order and you'll get the same answer. That's shown here in diagrams. Subtraction, okay, subtraction is really a cousin of addition. All you have to do is define the negative of a vector. So when you say A minus B, if you understand what is minus B, which you already do because you already saw that, A minus B is the same as A plus of minus B. Okay. So once you know addition, you know subtraction as well. Okay. You guys understanding this? I'm not going too fast or anything. All right. So we're going to mix things. Scalar multiplication. We're going to multiply a vector by a scalar. Okay. And you already know that. So we did this. Here's a vector, and we are multiplying that by a scalar. So all you did was that scalar, it multiplied the magnitude of that. Okay, so it's a vector 3 times as long in the same direction. And of course, you know what 3/4 A means. It's 3/4 the length in the opposite direction. Okay. Okay, now we'll get to the nuts and bolts. Okay. We'll introduce three special friends. We'll do stuff in 3 dimensions. And so we'll introduce these unit vectors. Yeah, they're special guys. What do you think the unit vectors mean? What does that? I'm sorry? So the magnitude of these vectors is 1 unit. Okay? How many unit vectors are there in 3 dimensions? I'm sorry? There are an infinite number of unit vectors. Okay? We are interested in these 3 special guys. Okay? So this I is the unit vector along the x-axis, j is a unit vector along the y-axis, and k is a unit vector along the z-axis. All right, so you'll see in a second why these guys are special. Okay, what is this guy? Is he a vector or a scalar? I'm sorry? I'm sorry? It's a scalar. Okay, good. How about this guy? He's a vector. Yep. So this is a scalar multiplied by a vector. Okay. What is this guy? He's a vector. Okay. So okay, so we know the vector and oops. So what did we just write? Here's a vector, and we want to add this vector to that. Okay. And we know how to graphically do this. This plus that is this vector. So there we go. That was our destination. Okay. We've learned to write a vector in component form. Okay. So 5 is the x component. Okay. So the vector A, there's the x component. Okay. So here is a 2-dimensional vector. And of course, you can generalize this to as many dimensions as you want. Okay, so if A was a 3-dimensional vector, okay, that would be the 3-dimensional vector. Okay. Why do we do this? Because now adding vectors is very easy. Okay, so let's say you have A plus B, and let me write down B. So the rule is, if you're adding A and B, you just add the corresponding components. So you see, adding vectors has become so easy. You don't have to worry about drawing diagrams to scale. You don't need a protractor or anything, and you can solve problems fast. And not only that, This kind of stuff is easy too. Okay, you can add a whole bunch of vectors. This would be ax minus 2bx plus 3cx I. Who's going to help me with the y component?
A sub y minus 2b sub y plus 3c sub y.
Very good. Again.
Which is just the same thing except z instead of y.
There you go.
Okay.
So you suddenly have learned algebra. Okay? To do algebra with vectors. It's that easy. All right, so again, you use 3 mutually perpendicular unit vectors to make life easy. You don't have to have 3 mutually perpendicular vectors. Any 3 non-collinear, any 3 vectors. Okay, so 2 non-collinear vectors in one dimension and a third vector off the plane is good enough. But life would be tougher, so the easiest is when you have 3 mutually perpendicular vectors. Yeah. By the way, this is a right-handed coordinate system. We always use right-handed coordinate system. Again, and the right-handed coordinate system is like that. You're using your right hand. If this is your x-axis, that's your y-axis, that's your z-axis. Okay. You turn from x to y-axis. If you turn a screw like that, the direction in which the screw moves is the z-axis. Okay. The direction in which a right-handed screw moves. All right. Any questions so far? All right, so here's a vector A. This vector is that guy plus that vector. And you see there, so in this notation, instead of I, they've used x hat and y hat. So there's the x component, there's the y component. Okay, so the vector A is this vector along the x-axis plus that vector along the y-axis. Okay, so it's axi plus ayj. Okay, so ax, ay. Okay. Now in 2 dimensions, how many numbers do you need to specify a vector? I'm sorry? 2 numbers. Okay. So it turns out that you can give these 2 numbers, or you could give these 2 numbers, or any combination. A, ay, theta, or any 2 combination. Okay? And you're completely specifying the vector. Yeah. Now the polite thing to do is, of course, give these numbers or those numbers. Okay. So that's what's generally done. Okay, so you're either given the components or you're given the magnitude and direction. Okay. And oftentimes when you're given this, you'll need to convert to the components, or if you're given the components, you'll need to find the magnitude and direction. Okay. And that's what these formulas do. So the components, so you're given the magnitude and direction, and there's how you find the components. Okay? Magnitude and direction, there's how you find the y component. Now for these formulas to work, the angle is measured from the x-axis counterclockwise. Okay, that's the positive direction. So these formulas will work as long as you're measuring the angle counterclockwise from the x-axis. Okay. If you measure it clockwise, that's a negative angle. Okay. So these formulas let you go from this direction to that direction. These 2 formulas let you go from this to that direction. So given the components, there's the magnitude, and there's the angle. Okay. Now, this tan inverse function is a multi-valued function. See, for instance, tan inverse of minus 5 over 4 is equal to tan inverse of 5 over minus 4. You guys see that? See, that's a negative y component, positive x component. That's a vector in the third quadrant. This is a vector in the second quadrant. Okay. You get the same. So based, and we'll get to this when we do problems, but you just have to be aware of that and decide what angle it is that's the correct answer. So this tan inverse of a number, it has two solutions. It's theta or theta plus 180 degrees. And then you decide based on your components. Okay? Again, we'll come to that. So here's a vector A. We're talking two-dimensional vectors. Okay, so if both components are positive, if AX and AY are positive, then the vector is in the first quadrant. If AX is negative and AY is positive, it's in the second quadrant. If AX and AY are negative, the vector is in the third quadrant. AX is positive, AY is negative, that's in the fourth quadrant.
It's just lagging a little bit.
Well, this is not good.
It wasn't happening until,
It just happens every once in a while.
yeah.
Hmm.
So
Most of the time, it's not,
Yeah.
That's still writing it down.
That's not such a
That's almost a 5-second lag.
Yeah, it's still,
What's that?
yeah. It's almost caught up.
I guess I'll have to talk to the IT guys. All right, any questions? I can pause here a second. What's that?
It's going smooth again.
Okay. All right, so now you know, now that you write vectors in component form, now that you've learned how to write vectors in component form, adding and subtraction and all that is very easy now. Okay, so if you want to add two vectors, you just add the corresponding components and so on. Okay. Now, underneath all of this, okay, when you add two vectors, when is the length of the sum equal to the sum of the lengths? So,
Pointing in the same direction.
very good, my friend. Okay, so that was what was underneath there. See, when you're adding these vectors, what is this? There's 4 vectors that you've added. Each one is a vector. You added this vector plus this vector plus this vector. And what did you do here? Well, this vector and this vector were pointing in the same direction, and so you could add their magnitude. That's all you did. Okay. In other words, okay, so you can think of them as like terms, and you added like terms. Okay. All right. So you know how to add vectors. So again, statements and laws in physics are expressed as equations. So here's a kinematic equation that's giving you the final position is equal to initial position. The subscripts are telling you that. That's the initial velocity times time plus 1/2 at squared. And here's Einstein's general theory of relativity. Okay. Okay, it took us 1 hour to learn how to add vectors. Now we're going to learn how to multiply them. Okay? Now, So let's say this right off the bat. Numbers, there's only one way of multiplying vectors. Okay, I mean one way of multiplying scalars. Now vectors are a little more complicated objects, and it turns out that there are many ways of multiplying them. I mean, you can define many ways of multiplying them. We are interested in two ways of multiplying vectors that are useful to us. Okay. One is called a scalar product or dot product. So the name suggests this is called a scalar product because the answer is a scalar. Okay. So again, in 3 dimensions, how many numbers do you have for a vector? 3. So you're going to take two vectors that are 3 numbers each. You need 3 numbers each to specify them. You're going to multiply them and come up with one number, a simpler object. Okay, so that's a scalar product. Okay, it's called a dot product because the way the notation is. Okay, so A dot B is defined as, so here's a vector A, here's a vector B. A dot, and you're drawing the vectors from the same point, and there's the angle between them. So A dot B is defined as the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay, that's a scalar, scalar, scalar. So that's a scalar. Okay, so the product of 3 scalars is a scalar. And you can see that the dot product can be positive or negative. Okay, the maximum value of the dot product is when theta is 0 or phi is 0. Okay, so when they're pointing in the same direction, then the dot product is just the product of their magnitudes. When phi is 180 degrees, that's when the dot product is the minimum value. Okay. All right. So here's the dot product given in terms of components. Okay, so both these definitions will be useful. Okay, again, this is a scalar plus a scalar plus a scalar is a scalar. Okay. Now, the reason we are learning this is you'll learn when you push something and the object moves, then you're doing work on the object. Okay, so for instance, if you apply a force on the object and it moves a certain distance, the amount of work you've done on this object is F dot S. Okay. So that's, you will learn that the work is a dot product of the force acting on an object dotted with the displacement. Okay. Now here's another vector product that is useful. This is a vector product, so the result is a vector. Okay. And it's also called a cross product because of the notation. So this is also called a cross product. Okay. All right, so C is A cross B. Okay. So now we want to know what C is. Okay, how do you find C? All right, first let's do the directions. Okay, so you use your right hand. Okay, and if your thumb is the first vector, there is the second vector. You turn from the first vector to the second vector. C is pointing in that direction. Okay, so here's a couple of things. C is perpendicular to the plane containing A and B. Okay, now you just have to figure out either this direction or that direction, and you use your right hand to figure out the direction. Okay. Now there will be times when you won't be able to twist your arm, so here is a good way to remember this. Okay, and you'll need to do this. So here is the first vector, second vector. If you turn from the first vector to the second vector, which way does the screw move? That way. And that's the direction of vector C. If it's like this, the screw moves down, that's the direction of C. If this is A, if you turn the screw this way, the screw moves this way. That's the direction of C. Okay? That's the best way to remember it. Okay. So figure out the direction in which the screw moves. Okay. So there, A to B, that's the direction. Okay. All right. So again, the important thing is when you're taking the cross product is perpendicular to the plane containing these two vectors. Okay. All right. So we have established that. So there's the plane and it's perpendicular to the plane containing them. All right. Now I'll show you how I remember it. But when you do determinants, here you can write this in terms of determinants. Okay, so there's the cross product. Okay, so, but here's how I remember it, how I like to remember it. Okay. So you write I or I, J, K. You draw your circle with I, J, K. So the X component is AY, BZ, AY, BZ, and the negative of the flipped AZ, BY. Oh, is it up there now? Not yet? No, this is not good. All right, so the y component of this vector, that did it fast. So again, what would be the rule? So now you're trying to figure out the y component. It would be AZ, BX. Okay. AZ, BX. And then negative of the flipped. Okay, let's see if you guys can figure out the Z component. Anybody want to try that? Anybody want to give it a shot? So Z component is AX, BY. There you go. Okay, so here's a cross product of two vectors, and there's the resultant vector. Okay. So, and the reason we do this is so when you do physics 2, well, so you will learn about torques. Torques are cross product of this is the point, this is the vector to the point of application of the force. You're calculating the torque about the origin. You will, when you calculate the force on a charged particle in the presence of a magnetic field, this is the charge of the particle, that's the velocity of the particle, that's the magnetic field in which it is traveling. Okay, so you'll come across cross products in those two situations. Okay. Here's another one. Angular momentum is R cross linear momentum. Okay. So there'll be many situations where we'll calculate the cross product. This is not good. Go ask for your money back for today. Okay, the school owes you $15. That's what you're paying per class period. All right, so you guys understand cross products? All right, now here's another property. 4 times 5 is the same as 5 times 4, but it turns out that the cross product is anti-commutative. Okay, is minus b cross a. Okay, a cross b is not the same as b cross a. Okay. What this formula gives you is, what is this formula giving you? What is that notation? Very good. So it's giving you the magnitude of the cross product. Okay. And the magnitude of the cross product is magnitude of A times magnitude of B times the sine of the angle between the two. Okay. And A and B are drawn from the same point. Okay. So that's how that angle is defined. Okay. Okay, so we learned how to, what are these fellows? I'm sorry? Unit vectors. Okay, so now that we know cross products, it makes life easy if you know the cross products of vectors, if you remember them. I cross j is that, j cross k is I. Okay, so again, I cross j is k, j cross k is I, k cross I is j. Okay, so all right, quickly, what is I cross k? I'm sorry? What is, so k cross I is j. What is I cross k? Very good, negative j. Okay, you just learned a cross b is c, b cross a is minus c. Okay? All right, so it's good to remember this. All right, so let me give you a 5-second summary of what we just did. We learned a new mathematical object, a vector. And in n dimensions, you need n numbers to specify the quantity. 1 for magnitude and n minus 1 for directions. So in 3 dimensions, you need 3 numbers to specify the vector. And we learned how to add them, subtract them, and multiply them. And there are 2 ways of multiplying vectors. The scalar product, the answer is a scalar. And a vector product where the answer is a vector. When you're multiplying 2 vectors, the cross product, the vector product, is the vector that is perpendicular to the plane containing the 2 vectors. Okay? And you use your right-hand rule to figure out the direction. All right, guys. So